Hello, everyone. I'm Ozan. I develop applications at SignalFx. I'm going to be talking about getting some practical ways of getting more value from your data using analytics. So to start off with, let's talk about some common sources of operations data. The most unfortunate source of data is someone calling you to let you know that your system is down. If this occurs and you don't already know that your system is down, then there's clearly a huge gap in your monitoring. Luckily for us, in our industry, this is pretty rare, since there are many tools to fill that gap. So a common first step is to use a service like Outliers to periodically check your system and let you know when there's a problem. So executing HTTP requests and seeing if it returns the expected status code. This technology has been around for quite some time, with Nagios being about 17 years old. The data source that I'll be talking about is metric time series. So these are measurements from your infrastructures or applications or even business metrics collected and stored over time. Some examples are like CPU utilization, active database connections, or response latency. The data is unique in that it provides a rich space for real-time analysis so that we can better understand the current state of our system, find outliers, and forecast the future states of our system. Before we get to the more advanced use cases, though, let's consider a simple one, finding a typical value in our data set. So we could be collecting many thousands of measurements per second for metrics such as response latency. Reducing this to a single value acts as a focal point for discussions, monitoring, and comparison. So the most common way that I've seen this for many of us is using averages. Here's a simple graph of HTTP endpoint. So now we can say that during this week, our response time tended to be around 600 milliseconds, and it didn't vary much throughout the week. Averages have an unfortunate property in that they're prone to being influenced by outliers, heavily prone. So request timing is a common example of this. Most of our clients will behave similarly to each other, but you'll always have a few which are, due to external reasons, are exceptionally slow to respond to. So if the majority of our requests are coming in at less than half a second, but if you come in at 30 seconds, the average would take this into consideration when giving you the value. Medians are similar to averages in that they provide a typical value for our measurements without the side effect of being influenced by outliers. Since our goal is to find a typical value, outliers, by definition, shouldn't influence that value. So the median is the value that's in the middle of an ordered list of values. So half the measurements would be below this number and half would be above. So in this case, our distribution was such that the median, or the average was 50% more than the median. So that's the median is about 400 milliseconds, whereas the average was about 600 milliseconds. Finding culprits influencing the average is pretty easy. We just have to look at the edges of our distribution. In this case, we're looking at the max response times. So this is the pool that we're seeing on the average. So it's mostly at 10 seconds with a period on the 18th that's off the charts. For this type of data, the min and the max don't provide any useful information because it only takes one out of thousands or millions of measurements to make it onto this chart. That's not to say that understanding how slow our slow data isn't important. If we're interested in that, we can use something like the 99th percentile. This gives us the timing at the tail end of our distribution, so the slowest 1% of measurements. So whereas the maximum observed timings were around 10 seconds, the 99th percentile is around 5 seconds. And we can also see that whatever happened on the 18th that caused the max to go off the charts wasn't due to a general slowdown of the population. It didn't even impact the 99th percentile. So from a monitoring standpoint, it wasn't very interesting information. So let's consider a different type of metric, CPU utilization. In this case, we have about 100 servers reporting the metric, and that's a reasonable amount to plot directly. So now we can see that our servers tended to behave as a group. They varied between 10 and 20% for most of the week, ramping up to 30%. It's a fairly busy visualization with many sharp peaks, and it's not clear if this is due to the entire population moving up and down as a group, or if these are individual servers. So we can remove this noise by applying some smoothing. In this case, we'll do a moving average. So we're intentionally tossing away some information to get a clearer picture of the underlying data, or the underlying patterns. So now we can see that there were 2 sustained peaks throughout the week, along with a divergence in our servers at the end of the week. Now we can we can process this data further to highlight specific aspects or summarize the state down to a single value as we did before. If the servers were meant to share workload, then understanding the variation in CPU utilization is going to be an important thing. So standard deviation is a common way of doing this, a low deviation meaning that our CPU utilization was similar throughout the cluster, and a high deviation meaning that they differed significantly. The graph of the deviation is notable in that the divergence that we saw at the end of the week can now manifest itself as a significant increase in value. So this makes monitoring pretty simple because we can just draw a threshold line and say, alert us whenever we cross that. We can go a step further here by not only finding out when there's a divergence, but which servers are causing the divergence, so like where the outliers are. So as in averages, outliers have a strong influence or a disproportionate influence on standard deviation, which makes it unsuitable as a baseline for measuring outliers. So I'll go over another method of measuring variance called median absolute deviation, which is not prone to being influenced by outliers. So unlike standard deviation, it's uncommon to find this in visualization or monitoring platforms as a ready function, but so long as you can take a median and an absolute value, you can still drive it pretty easily. So we start off by subtracting the median value from each member, so the median CPU utilization from the CPU utilization, to get the deviation from the median, and then we're going to take the absolute values and find the median of this group to end up with the median absolute deviation. This is also referred to as MAD, but that can refer to both median and mean absolute deviation. So the values that we see here are less dramatic than what we saw in standard deviation, and we can interpret that to mean that the deviation that we saw was due to a small number of outliers rather than large representative within the group. We still see the impact at the end of the week, but it's not as pronounced as in the standard deviation. So now we can build a baseline by taking the median and adding a multiple of our variation on top. This is a similar idea as using mean plus standard deviation. Now we can compare this to our individual server CPU utilization to highlight the outliers pretty clearly. So if we were monitoring this, we would just configure the system to alert us whenever an individual server crossed our threshold, our dynamic threshold. But to visualize it, I just subtracted the 2, so anything that's above 0 would be considered an outlier. This is a general way of detecting outliers, so this isn't specific to CPU utilization at all. If we're interested in measuring deviation from a norm within any metric, we can use this method. So finally, let's take a look at another metric that we're all familiar with, disk utilization. In this case, we have about 40 servers across a few days, so it seems pretty flat. The methods that we looked at previously don't provide us much useful information, because in this case, I'm not interested in a characteristic of the population, but more of like when I'm going to run out of disk space. So the first step is to find the rate of change, how fast we're consuming disk space. Simple way of doing this is to take yesterday's disk space, subtract it from today's, to get a rate of change. So this is a bit more interesting, and it tells us that we're using about 0.2% per day, but it's not really useful information. It's not actionable. So we can take the amount of disk space that we have currently and divide it by the rate of change, or rate of consumption, to get the estimated number of days of disk remaining. So this is going to be far more useful monitored than visualized, but the visualization will give us an idea of whether our projection model is sane. In this case, our disk space consumption is linear, which works well with the simplistic projection model. We can then set up monitoring to let us know a couple of weeks before we run out of disk space so that we can remedy the situation before it becomes a problem. So hopefully this provides you with some practical ways to make better use of your metrics data. If you're interested in learning more about modern monitoring, come by and see us at the SignalFx booth. Thanks for listening.